Okay, thank you very much for the introduction and for the opportunity to speak in this seminar. So as my title indicates, I will be talking about abstract homomorphisms together with a few applications. So more precisely, I will present some results that address a conjecture of Berlants. I will mention a couple of applications to character varieties of finely generated groups. And hopefully, towards the end of the talk, I will also be able to say something about representations of certain non-arithmetic groups as well. OK, well, let me begin by saying a few words about the general philosophy in the study of abstract homomorphisms. OK, so suppose we have two algebraic groups, G and G prime, defined over fields K and K prime respectively, and we have an abstract homomorphism phi between their groups of rational points. Then this phi can often be written essentially as a composition of two maps, beta and alpha, where alpha is induced by a field homomorphism, alpha tilde from K into K prime, and beta arises from a morphism of algebraic groups. Now, whenever our abstract homomorphism admits such a factorization, we'll say that it has a standard description. And basically, one expects that under appropriate assumptions, all abstract homomorphisms should have a standard description. Now, in this talk, I will use the term rigidity statement to refer to any result that establishes the existence of standard descriptions. OK, well, the study of abstract homomorphisms is a rather well-established subject, and its origins go back, at least as far as I know, to the early part of the 20th century. But in the interest of time, I won't give a full historical overview. Instead, to set things up for the remainder of the talk, I would like to talk about some results of Berlants from their 1973 Annals paper on abstract homomorphisms. And one of the results that appears in that paper is the following theorem. Okay, so suppose, again, we have two algebraic groups, G and G prime, defined over infinite fields, K and K prime. And let's assume that G is an absolutely almost simple K isotropic group and G prime an absolutely simple adjoint group. Now, this K isotropic condition basically means that our group has lots of K rational unipotent elements. And therefore, it makes sense to consider the subgroup, which Berlants denote by G plus. It is, by definition, the subgroup of G of K generated by the K points of the unipotent radicals of K-defined parabolics. So informally, you can just think of it as the subgroup generated by the K rational unipotent elements if you want. And then what they show is that any abstract homomorphism phi of G plus into G prime of K prime, which has a large image, as a risky dense image, has a standard description. And in fact, they prove a similar but slightly more technical statement in the case that G prime is only assumed to be reductive. OK, so a natural question to ask at this point is the image of a semi-simple group on an abstract homomorphism always reductive? Well, the answer is no. And in fact, Berlants give an example of an abstract homomorphism phi such that G is an absolutely almost simple group defined over an infinite field K. The homomorphism has Zariski dense image, but G prime is reductive. Okay? So let me sketch for you the construction of this example. Okay, so we start with an absolutely almost simple group G over an infinite field little k. So for concreteness, we could work with a matrix group like SLN. The next piece of the construction is we consider a field extension big K of little k, which admits a non-trivial derivation. So we could just take big K to be the field of rational functions over little k, and delta to be just the usual operation of differentiation. And then we set our G prime to be the semi-direct product of G with its Lie algebra. And we define an abstract homomorphism phi in this way. Okay, so it looks a little messy, but basically the map capital delta is just obtained from the derivation little delta. So if we're working with a matrix group, all we do is just apply the derivation to the matrix entries. And then the fact that we're working over an infinite field implies that this homomorphism actually has a risky dense image. And basically, by construction, the unipotent radical of G prime is the Lie algebra G. So in particular, it's non-trivial. OK, so that's the construction of the example. Now let me give a more conceptual interpretation of this, which is also due to Berlants, and which is more relevant for our purposes today. OK, so let's consider the algebra of dual numbers over K, denoted by A. And let's define a map from K into A using our derivation. Well, then this, of course, is a K-algebra homomorphism. And therefore, it induces a group homomorphism on the groups of rational points. Furthermore, we have our usual identification of G of A with a semi-direct product of G with its Lie algebra. And finally, we recover our map phi as the composition of this group homomorphism capital F induced by our ring homomorphism little f, followed by the identification T. OK, so really the point of this example is that our homomorphism phi basically arises from a ring homomorphism, or in this case, an algebra homomorphism. And given the nature of this example, Berlants conjectured that any abstract homomorphism can be obtained in basically this way. OK, so let me be a little more precise about that. OK, so just as in the theorem, we consider algebraic groups G and G prime defined over infinite fields K and K prime. And now let's suppose that G is a semi-simple, simply connected group, which was certainly the case in the example that we saw. Next, suppose we have an abstract homomorphism rho between the groups of rational points. And let's assume that this homomorphism has a risky dense image. Then what Berlants conjectured is that there exists a finite dimensional K prime algebra B together with a ring homomorphism F from K into B such that our abstract homomorphism can be factored as a product of the following three maps. OK, so here I again use the notation capital F to denote the group homomorphism induced by the ring homomorphism little f. Sigma is a morphism of algebraic groups. And R is just the usual identification that we get from the functorial restriction of scalars. OK, so this R shouldn't really frighten you. It's basically there just for formal reasons. The content of the conjecture is that we should be able to write our abstract homomorphism as a homomorphism arising from a ring homomorphism, followed by a morphism of algebraic groups. OK, so that's the conjecture that appears in the paper of Berlants. Just one small remark. So in that conjecture, Berlants do not explicitly put any restrictions on the characteristics of their fields. But they sort of do informally caution that maybe some restrictions may be necessary. And in fact, using some of the theory of pseudo-reductive groups over imperfect fields of characteristic 2, Brian Conrad and Gopal Prasad were able to produce some counterexamples. So that's basically just a consequence of some exceptional isomorphisms. And presumably something similar can also be done in characteristic 3. So one has to be a little careful with small characteristics. OK, well, as we've seen, the theorem of Berlants handles the conjecture in the case that G prime is a reductive group. So what if G prime is not necessarily reductive? Well, shortly after the conjecture was formulated, it sketched a proof in the case that K and K prime are both the field of real numbers. And he published this argument in some conference proceedings. So really, the argument is very much a sketch. And I don't think he ever returned to this result again. So there's really no full-length exposition as far as I know. And also, Lucy Lifshitz and Andrei Rapinchuk essentially proved the conjecture in the case that K and K prime are both fields of characteristic 0. G is a universal Chevalier group, and G prime is a group with commutative unipotent radical. OK, so that was sort of the status of the conjecture. Now, one thing that I should point out is that the theorem of Berlants, as well as the conjecture, deals only with groups of points over fields. But another direction which has received quite a bit of attention over the years, both for its own sake and also in view of various applications, has been the analysis of abstract homomorphisms of groups of points over various rings. And of course, most of the attention has been focused on rings of number theoretic origin.
So, since these are now probably different methods, can you say a word about methods?
Yeah, so basically the methods involve more or less studying where unipotent elements go and trying to derive some information about the fields from that.
If you drop the split, so if you don't have unipotence, you can't proceed.
No, certainly their argument doesn't go through. And in fact, as I'll explain, my method, it's quite different from that of Berlants, but it's also based very essentially on the study of where unipotent elements go. So yeah, without those, it's not clear what to do. Okay, so there have been quite a number of directions in the study of abstract homomorphisms over various number rings. So let me just mention a couple. So Botts, Milner, and Serre used their solution of the congruent subgroup problem to establish some rigidity statements for groups like SLNZ, SP2NZ, and so on. And of course, one has the powerful results of Margulis's superrigidity theorem for lattices in high-rank Lie groups. And in fact, I'll sort of revisit these results from a slightly different perspective towards the end of the talk.
Of course, the last doesn't provide.
It doesn't, yes, but unfortunately, those methods do not go through when we deal with sort of more general commutative rings. Yeah. Okay, and well, in fact, the first result that I will present deals sort of with the natural extension of the conjecture of Berlants to this more general context of studying abstract homomorphisms over rings. And I will also continue to use the terminology I introduced on the first couple of slides, so standard descriptions and rigidity statement will be understood in this more general context. Okay, perhaps before I wrap up this introductory section, I should say that although this work is of a purely algebraic nature, this whole story also has a very important geometric side to it. So perhaps one of the most famous statements there, and really the result that got everything going, is Mostow rigidity, which in its geometric formulation says that closed hyperbolic manifolds of dimension at least 3 are determined up to isometry by their fundamental groups. But of course, that would take us in an entirely different direction. So for the remainder of the talk, I will focus on the purely algebraic aspects of the story. Okay, so any questions before I move on to talking about some of the results? Okay, so as I said, the first result that I will present addresses the conjecture of Berlants for split groups over commutative rings. So first, let me fix some notations that we'll actually be using for the remainder of the talk. Okay, so we'll take K to be an algebraically closed field, R a commutative ring, and phi a reduced irreducible root system of rank at least 2. Okay, so I will need to impose some assumptions on the units of the ring. So let me introduce this terminology of a nice pair. So we'll say that the pair phi r is nice if 2 is a unit R if phi contains a subsystem of type B2, and 2 and 3 are units in R if phi is of type G2. Okay, next we'll work with a simply connected Chevrolet group over Z of type phi, and I will denote by G of R plus the so-called elementary subgroup of G of R. That is to say, the subgroup generated by the R points of the canonical one-parameter root subgroups. Now, whenever we have a finite dimensional commutative K algebra, we'll treat G of B as an algebraic group over K using restriction of scalars. And one final bit of notation is the following. So suppose we have an abstract representation rho of our elementary subgroup. then I will use H to denote the Zariski closure of the image, and H0 will be the connected component. OK, so let me now formulate the first result. So suppose we have a nice pair phi r. And moreover, let's assume that R is an Noetherian ring if K happens to be a field of positive characteristic. And let's take a representation rho of our elementary subgroup. Then, in each of the following situations, so if the image is reductive, or if K is a field of characteristic 0 and R is a semi-local ring, that is to say has finitely many maximal ideals, or finally, if K is a field of characteristic 0 and the unipotent radical of H0 is commutative, then there exists a finite dimensional commutative K algebra B together with a ring homomorphism F from R into B with a Zariski dense image, as well as a morphism sigma of algebraic groups from G of B into H, such that on a suitable finite index subgroup, our representation coincides with the composition of sigma and F. So here, again, I use capital F to denote the group homomorphism induced by, H, so yeah, it's the Zariski closure of the image of my representation. Right, so in the theorem of Berlants, they assume that their homomorphisms have Zariski dense image. I'm just taking the Zariski closure of the image. So. OK, so basically, what this is saying is that under some assumptions, our representation can indeed be factored as a group homomorphism arising from a ring homomorphism and a morphism of algebraic groups, at least after passing to a finite index subgroup.
In terms of, say, superrigidity would give you what in this kind of situation?
Yeah, so actually I'll address this a little later in the talk. So if we, for example, take our ring R to be a ring of integers or S integers, this would mean that we actually don't need to impose any additional assumptions. The statement would simply be that any representation has a standard description. And in fact, the algebra that occurs is just a product of several copies of the field K. And the homomorphism is just basically restrictions to the ring of integers of embeddings of our field. Yeah. So yes, I will return to this a little later.
So the fact that superrigidity is being established in the rank 1 situation, that's something you could exploit?
Unfortunately not. So
You need these unipotents?
yes, I need unipotent elements and also actually need, well, the rank to be at least 2 because I work with commutator relations and it's simply impossible. Well, I mean, it might be possible, but it becomes quite a bit more messy to try to do it in rank 1. OK, so right, so that's the result. Well, if we want to make it a little more concrete, perhaps one thing that we should try to do is attempt to understand what kinds of algebras can arise in this situation. And again, I mean, in the theorem of Berlants, one only has to deal with fields and embeddings of fields. But over rings, there are, of course, many more possibilities. So let me not try to consider the most general situation, but rather let me work with the ring Z box X. And let's assume that the field has characteristic 0. And also, let me fix S distinct non-zero elements of my field. Well, of course, the simplest kind of algebra that could come up, and in fact does come up, is just a product of several copies of the field K. And in this case, our homomorphism F is basically just an evaluation map. That is to say, we take a polynomial, and we evaluate this at these points A1 through AS. And these are the kinds of algebras that come up when we consider representations with reductive image. OK, now if you think back to the example of Berlants that I presented in the first part of the talk, there our algebra was the algebra of dual numbers, and we worked with a single non-trivial derivation. So we can spice things up a bit and work instead with several copies, with a product of several copies of the algebra of dual numbers and several linearly independent derivations. And so in this particular example, our derivations are simply taking the derivative followed by evaluation at our points. And these are precisely the kinds of algebras that come up when we deal with representations whose image has commutative unipotent radical. Another way we can extend the example of Berlants is, instead of working with several derivations, we can work with powers of a single derivation. And then our algebra is this thing, so it's generated by a single nilpotent element. And the homomorphism is just a truncated Taylor series. OK, so well, from these examples, we see that the images of the root subgroups can have arbitrarily large dimension. And also, whereas the example of Berlants only gave us representations with commutative, whose image has commutative unipotent radical, using this last kind of construction, we can produce representations whose image has unipotent radical of prescribed nilpotence class. Actually, this was carried out in detail in the paper of Lucy Lifshitz and Andrei Rapinchuk that I mentioned earlier in the talk. OK, so how do we deal with all this variety that can possibly arise? Well, our first step is to associate a so-called algebraic ring to our representation. And in doing this, we generalize a construction which Martin Kasabov and Mark Sapir carried out for SLN. Next, one needs to say something about the structure of these algebraic rings.
Are you going to explain it?
Oh, yeah. So I'm going to go into the details. Yes, absolutely. I'm not going to leave you hanging at this point. Yeah. And then we have to apply some results of classical K-theory. And I should also say that although I've formulated the results only for groups over commutative rings, one can use a similar kind of analysis to obtain rigidity statements for elementary groups of type AN over certain non-commutative rings. So for example, that gives rigidity statements for groups like SLND, where D is a finite dimensional central division algebra or field of characteristic 0. And in fact, that suggests sort of a strategy for handling all groups of relative rank at least 2. OK, so the application of K-theory involves more or less standard results, so I won't really say anything about that. Instead, I'd like to tell you a little bit about this algebraic ring and the analysis of the structure. OK, well, an algebraic ring is basically what the name suggests, namely an affine, well, an algebraic variety with a ring structure defined by regular maps. OK? A little more precisely, we'll say an algebraic ring is a triple A alpha and mu, where A is an affine algebraic variety over a field K, and alpha and mu are regular maps from A cross A into A, which one should think of as addition and multiplication, such that A with the operation alpha is a commutative algebraic group, and alpha and mu satisfy the usual associativity and distributivity axioms. And of course, one can consider both commutative and non-commutative algebraic rings, but for the purposes of this talk, I'll just stick to the commutative case. OK, so now let me tell you how one can associate an algebraic ring to our representation. And just to keep things as concrete as possible, I will work with the group SL3, although the strategy in the general case is technically more involved, but it's in the same sort of spirit. OK, so let's consider a representation of our elementary subgroup. And let's set H to be the Zariski closure of the image. OK, so remember, we're trying to construct our algebraic ring A. OK, so as an algebraic variety, we take A to be the Zariski closure of the image of any root subgroup. It really doesn't matter which one. For purposes of exposition, let me just fix the root subgroup E13. OK, so then we define the addition operation to be simply the restriction of the matrix product in H to A. And in this way, we obtain a commutative algebraic group. And if we define a map F from R into A in the natural way, then we get a homomorphism of abelian groups. Okay, so that's the addition operation. Nothing really too exciting going on so far. Now for the multiplication operation, we'll need these two elements. So what are they? Well, they're basically just lifts of Weil group elements to our elementary subgroup. And they, I mean, in this case, one can check this by direct computation that this is how they act on our root subgroup. Now, really, the key to defining the multiplication operation turns out to be this well-known commutator relation between the root subgroups E12 and E23. OK, so now let's define a regular map from A cross A into H in the following way, right? So we apply our Weil group elements and our representation, take the commutator. And then we see that if we have this map F from R into A, then mu actually preserves the image of this map. And therefore, the image of mu lies not just in H, but actually in A. And then finally, using the fact that we're starting out with a commutative ring, and by construction our map F has a risky dense image, we obtain an algebraic ring with these operations alpha and mu. Okay, so in this way we can associate an algebraic ring to our representation. As I said, in the general case, the construction is fairly similar. So again, we take this risky closure of the image of some root subgroup. It actually doesn't matter which one we take. So short root, long root doesn't matter. And then, so again, we define the addition via the matrix multiplication. And for the multiplication, we need to exploit the so-called Steinberg commutator relations. Okay, so well, the point of the construction is that we can associate an algebraic ring to our representation that captures information about the images of all root subgroups simultaneously. OK, so we have our algebraic ring now. Let me now say a little bit about the structure of algebraic rings. So first notice that a finite dimensional K-algebra, of course, has a natural structure of an algebraic ring. In characteristic 0, it turns out that this is basically the only way to obtain algebraic rings. More precisely, suppose we have an algebraic ring over our field K, and let's assume that K is a field of characteristic 0. Then our A splits up as a direct sum of a finite dimensional K-algebra B and a finite ring C. Okay, so in particular, okay, I mean, one needs to do a little more work, but ultimately what we obtain is that there is an equivalence of categories between connected algebraic rings over fields of characteristic 0 and finite dimensional K-algebras. So let me just summarize what we've seen so far. Okay, so we start with our representation rho, and we associate an algebraic ring to it. Then, if we're in characteristic 0, our ring A splits up as a finite dimensional commutative K-algebra B and a finite ring C. So this algebra B is actually precisely the algebra that appears in the statement of the rigidity theorem. And you know, the possible existence of a non-trivial finite ring C is what forces us to pass to a finite index subgroup. OK, so that's the story in characteristic 0. Now, in positive characteristic, it's probably not too surprising that the correspondence between algebraic rings and algebras breaks down. OK, so again, I just want to be as explicit as possible about this. So let's consider the following example. OK, so let's take our algebra A to be the product of two copies of the field K with the usual component-wise addition, but with multiplication defined by this formula here. So, well, we certainly have an algebraic ring, but one can check, due to the presence of this exponent p, that this thing is actually not a K-algebra. However, it is closely related to a certain K-algebra. Okay, so again, let's take two copies of the field K, again with the usual component-wise addition, but now with a multiplication defined in a slightly simpler way without those exponents p. Okay, so what is this? Well, this is actually just the algebra of dual numbers. So in particular, it's a K-algebra. And we also have a natural ring homomorphism between A prime and A, defined in this way. So this is, of course, a morphism of algebraic groups. And actually, it's an isomorphism of abstract rings, but unfortunately not an isomorphism of algebraic rings. And in joint work with Mitya by Archon Kelly, we actually showed that this is pretty much what happens in the general case. Namely, suppose we have a connected algebraic ring over a field K of characteristic P, and let's assume that A is annihilated by P. Then what we show is that there exists a finite dimensional K algebra B and a morphism of algebraic rings from B into A, which is an isomorphism of abstract rings. Okay, so of course this is not quite as good as what we have in characteristic 0, but nevertheless it's sufficient to extend some of our results to positive characteristic. In particular, we're able to give sort of a short conceptual proof of a rigidity statement due to Gary-Zeitz, which was originally proved using techniques similar to those of Berlants. Okay, so this is just an overview of how we can apply algebraic rings to study abstract representations of these elementary subgroups. Next, I would like to talk about a couple of applications of these results to the analysis of character varieties of some finitely generated groups. And before I state anything, I should say that at least for me, these applications were one of the motivations for trying to understand representations with non-reductive image. Okay, so let me just fix some notations. Okay, so let's suppose that gamma is a finitely generated group, and K is an algebraically closed field of characteristic 0. Okay, then for each positive integer n, we can associate two algebraic varieties to our group. So the first is the nth representation variety, which is just the variety of all n-dimensional representations of our group. And the second is the nth character variety, which is just the quotient of the representation variety by the natural adjoint action of GLN. So basically, this is just the variety of all characters of representations. So in our applications, we'll assume that R is a finely generated commutative ring, and phi is a reduced irreducible root system of rank at least 2. Then Yershov, Heikin, and Kasabov have shown that the elementary subgroup of the corresponding Chevalier group has Kazhdan's property T. So in particular, it's a finely generated group. So as far as I know, I mean, this finite generation property, at least in some cases, can also be derived from some computations in classical K-theory. But this sort of gives a nice conceptual approach to that. Exactly, yeah. So yeah, in fact, I mean, when they started this work, they were actually just basically considering, polynomial rings or certain non-commutative generalizations of that. Exactly. Yep. Yep.
And that finite generation was not obvious there?
Well, so right. So if the rank is sufficiently large, then like at least 5 or something like that. So there was some work of, I think, Riemann and others in classical K-theory where they actually showed a finite generation property for the Steinberg group, and hence one also has finite generation for the elementary subgroup. But I think, so I'm not really an expert on the K-theory, but my impression is that they were not able to handle sort of rank at least 2 with those methods. Okay, so we can look at the representation and character varieties of such groups. Okay, and for the statement of the first result, we again take R to be a finite generated commutative ring, and moreover, we'll assume that phi R is a nice pair. So remember, that's just some condition on invertibility of 2 and 3 in certain cases. So it's not terribly important. OK, so the first result is that the dimension of the character varieties grows at most linearly in n. OK, so more precisely, what we show is that there exists a constant c depending only on the ring R, such that the dimension of the nth character variety is bounded above by c times n for all n. And this constant c is actually not terribly mysterious. It's really just related to a certain space of derivations of the ring R. In particular, if we work with a ring of integers or s integers, then the c turns out to be 0, and therefore our group is what is called SS rigid. That is to say, it has 0-dimensional character varieties in all dimensions.
That doesn't follow this from
so probably, I mean, you could derive it from some more classical statements, yeah, but I just want to mention that as a concrete application, yeah. Right, so I mean, yeah, probably one can derive it from something like superrigidity and complete reducibility of representation, yeah, so. OK, well, so what's the strategy of the proof? Well, it actually goes back to some work of André Weil in the 1960s. Exactly, yes.
Proof is not based, by the way. That's used to come out with some
OK, yeah, I mean, I learned it from the papers of André Weil.
Then he gave a nice calculation, which is chronological.
Right. So, yeah, so I mean, that's the version of the proof that I'm aware of. And so the idea, as in that proof, is basically to relate the dimension of the tangent space to the dimension of a naturally associated cohomology group. OK.
Mostow in Selberg's 70th birthday wrote a paper explaining that Selberg's proof works in all cases.
Oh, OK. Yeah, I was not aware of that. OK, and so once we make this connection to this cohomology group, then basically what we want to do is to exploit our standard descriptions for representations with non-reductive image. So specifically, we just deal with a case where the unipotent radical is commutative. And we're able to relate this cohomology group to a space of derivations of our ring R. So that's basically a sketch of how we get the linear bound. Now, one thing that is more speculative now is, well, essentially all known examples of discrete linear groups having Cauchy-John's property T are, well, of this form. They're these elementary subgroups. And so a natural question to ask is it possible to derive this linear bound just from Cauchy-John's property T without using the additional structure that we have in this particular example? OK, so maybe it's better to call it a question rather than conjecture. But in any case, suppose we have a discrete linear group having Cauchy-John's property T. Then, can we give a linear bound on the dimension? OK, so let me just put this statement in context a little bit. So if our group happens to be a free group, then one can check that the dimension is quadratic in n. Exactly. OK, so, well, it follows that the rate of growth of this dimension function is at most quadratic. On the other hand, one can show that if gamma is not SS rigid, then the growth is at least linear in n. OK, so this conjecture, if true, what it would basically do is to characterize Cauchy-John groups as those groups having the minimum growth possible. And in some sense, that would be sort of the best possible rigidity statement for such groups.
How do you get below that?
Yeah, so it's actually really in a much different spirit from the rest of the talk. So perhaps.
Some deformations and some
Well, no. I mean,
computing these dimensions.
Yeah, it's basically just a direct computation. Yeah. So, but it's really in a very much different spirit. So.
You don't know much about gamma, so somehow you get it to G through some.
Yeah. So basically, one of the key things that we need for the argument is that if we have a completely reducible group of one of these groups having Cauchy-Duns property T, so in particular it has the property that the abelianizations are finite. And if we look at a completely reducible representation, there are only finitely many possibilities for the Zariski closure of the image of the representation. So that's one of the arguments that is needed. And then we sort of build up this linear bound by looking at suitable products of such of representations of this group. Yeah. And just maybe to sort of conclude this talk about this discussion of these dimension functions, well, we have groups where the rate of growth is linear, and also groups for which it is quadratic. So one can ask is there something in between? And this question was answered in the affirmative by Martin Kasabov, so I have the precise statement of his result here. But basically what he showed is that any function whose growth is between linear and quadratic can be realized as one of these dimension functions for a suitable finely generated group. Okay. Yeah, so what it is he looks at the direct products of groups SLN of Z, I believe, with n from like 3 to infinity. Okay, and he constructs a funny group which contains direct sums of such construct from such products. And he also is able to control the behavior of the finite dimensional representations of such a group. Yeah. Okay, so that was the first application to character varieties. The second application that I'd like to mention has to deal with realizing affine varieties as character varieties, so finely generated groups. Okay, so if we have a character variety, can we realize it as if we have an affine variety, can we realize it as a character variety for some finely generated group? And of course, depending on the application one has in mind, one can also impose some additional conditions on the group. Well, certainly one thing that we can't get around is the fact that character varieties are affine varieties defined over Q. So are there any other restrictions? Now, just to put this in a little bit of context, so this question is not entirely out of the blue. So it was actually an essential element in the work of Kapovich and Milson on Serre's problem of which finely generated and finely presented groups can arise as fundamental groups of complex algebraic varieties. And in their work, they answered this question up to basically birational isomorphism. So what they showed is that if we have an affine algebraic variety S defined over Q, then there's a certain finely generated Archon group such that a Zariski open subset U of our variety is biregularly isomorphic to a Zariski open subset of a suitable character variety of this group. Now, using our results on standard descriptions, I'm able to answer this question basically up to biregular isomorphism. Okay, so what I can show is that if, again, we have an affine algebraic variety S defined over Q, then there exists a finely generated group gamma having Cauchy-Duns property T and an integer m such that there is a biregular isomorphism between our variety and the complement of the trivial representation in our character variety.
Wait a minute. So you are answering your question even imposing property T.
Well, so it actually falls out of the construction that this group happens to have Cauchy-Duns property T. So that's kind of an added bonus.
So the answer is positive and you can make it infinite.
Yeah.
Shock. I would have
Okay, so let me just tell you about the main elements of the argument. Okay, so recall that our variety is defined over Q, so we can consider its ring of Q-defined regular functions. And inside that, we can pick out a finely generated ring, which generates everything when we extend scalars to Q. And okay, so it may be necessary to further localize our ring so that we eliminate this finite algebraic ring that I talked about earlier in the talk. Okay, then we take our group to be sp2n. And as our finally generated group gamma, we take the elementary subgroup of this group. And sort of the main input from representation theory that we need here is that, well, this group sp2n has just a single non-trivial representation in dimension 2n, namely the standard one. And using that, we're able to obtain this biregular isomorphism. Okay. So these are some applications of the results to the analysis of character varieties.
Is there some way of removing that open condition to make it more of a challenge so that the varieties have some nice? I mean, this is saying that character varieties are as bad or as good as.
Exactly. So that was sort of the idea of Kapovich and Milson in their paper, that, you know, if you take character varieties of these fundamental groups, then they can control sort of the singularities that arise. But the point that they observed is that it's possible to construct character varieties which are as nasty as you can imagine. So therefore, there are some finely generated groups which do not arise as fundamental groups. Yeah.
Then I'm asking if you, that seems to me like you put an open condition which then allowed you to do this too freely. It's not rigid. Somehow, if the character variety was globally, okay, I'll ask you.
Okay, yeah.
Because I'm not happy. I'm disappointed with the truth.
Okay, so unless there are any other questions, so let me now move on to the last part of the talk. As I mentioned in the introduction, I would like to first revisit some of the classical rigidity statements for elementary groups of a ring of integers. And then I will also indicate how our analysis enables us to address some questions for representations of certain non-arithmetic groups as well. Okay, so let me just remind you of the notation that I'm using. Right? So phi is a reduced irreducible root system of rank at least 2. G is the corresponding Chevalier group. And we'll work with various commutative rings R that I'll specify in the statement of each result. But even if I don't say so explicitly, we'll always assume that we have a nice pair, which, again, just is a condition on invertibility of 2 and 3. Okay, so it turns out that from the rigidity theorem that I had early in the talk, one can derive the following classical theorem. So suppose that we have a ring of S integers and a number field, then any abstract representation of our elementary subgroup has a standard description.
Because you used the theorem.
Well,
you used the theorem which implies that in your proof, aren't you?
well, no. So actually, let me explain how the theorem that I had in the beginning actually implies this. So it's not a circular argument.
But this theorem coming then, you extending the representation, saying it's standard, it's more or less that it extends to the group homomorphism.
Exactly, yeah. So, but the thing that here, remember in the statement of the theorem I had earlier in the talk, I imposed some conditions on the representation, like, for example, it had the image has commutative unipotent radical or whatever. So here, what I'm saying is that the conditions are actually, well, one of the conditions that I'll mention in just a second is satisfied automatically. And so therefore, our theorem sort of guarantees a standard description for any representation. Yeah. Okay, so if we want to derive this statement from the earlier result, the key point is just to note that our ring of integers has no non-trivial derivations. Okay, and that actually implies that the image is automatically reductive, and therefore the algebraic ring associated to our representation, or rather the finite dimensional algebra part of it, is just a product of several copies of the field K. Okay, and so this was actually one of the conditions under which the theorem guaranteed a standard description. Of course, this is entirely classical, but the point is that the strategy of looking at derivations also allows us to handle rings having few derivations, in a sense that I'll specify in just a second, and thereby we can obtain rigidity statements for some non-arithmetic groups, which, as far as I know, have not been handled using other methods. Okay, so let me just be a bit more precise about the kinds of derivations I'm talking about. Okay, so suppose we have a ring homomorphism G from R into K. Then we'll consider the space of derivations of R with values in K with respect to this map G. So what this is these are simply maps which are additive and which satisfy this version of the product rule. Okay, so the first result is that if the dimension of these spaces of derivations is at most 1 for all ring homomorphisms, then any representation of our elementary subgroup has a standard description.
When you're saying not, the point is that the ring R is not like I'm thinking of integers, it's polynomial rings, is that so that otherwise everything's arithmetic.
Exactly, so these are polynomial rings. So as a corollary of this statement, we obtain that any representation of SLM O box X with M at least 3 has a standard description. So, so we don't need to impose any assumptions on this representation. It always has a standard description. Exactly, yeah. Okay, so let me just indicate a few points of the proof. Okay, so as before, we said H to be the Zariski closure of the image, and let U be the unipotent radical of H0. So now, if you recall from the theorem that I had in the first part of the talk, that said that we have a standard description if U is commutative. Well, in fact, what the proof shows is that our row has a standard description if this condition Z is satisfied. So what it says is that the center of H0 has trivial intersection with a unipotent radical. And in order to verify condition Z in our situation, there are two ingredients. First, we show that the algebraic ring associated to our representation splits up again as a commutative K-algebra in a finite ring C. And moreover, the K-algebra is a product of several factors, each of which is generated by a single nilpotent element. So that's one thing. Another thing is that we need is an observation of Gauber, which says that if we have one of these algebras generated by a single nilpotent element, then any central extension of G of A tilde by a vector group automatically splits. Okay, and in fact, I should say that it's actually possible to produce some non-split extensions in the case that our algebra is generated by at least two nilpotent elements. And therefore, that leads one to believe that if we work with polynomial rings in at least two variables, then it should be possible to construct representations which fail to have a standard description without additional assumptions. Okay, so a couple of things that I'd like to point out about these representations over polynomial rings, where our coefficients are a ring of integers, is that, first of all, the restriction of any such representation to the elementary subgroup over the ring of integers is completely reduced. And secondly, any representation of such a ring, when restricted to the ring of integers, is 0. So in fact, if we take these 2 points, these 2 observations as our starting point, we can formulate a more general statement. First, just one more additional piece of notation. So if our ring R happens to be a commutative K-algebra over some little k, then we'll consider the space of those derivations which vanish when restricted to little k. OK, so now, again, suppose that these spaces are at most one-dimensional for all ring homomorphisms G. Then any representation rho of our elementary subgroup, which is completely reducible when restricted to the elementary subgroup over this little k, has a standard description. And as a concrete consequence of this, let me just mention the following result. So suppose that C is a smooth affine algebraic curve over a number field k, and we take R to be its coordinate ring. So then any representation of the elementary subgroup over this ring has a standard description. Okay, so we see, so first we saw how one can apply some considerations involving algebraic rings to the analysis of these representations. And now if we put in a few additional considerations involving derivations, we're able to obtain some rigidity statements for some non-arithmetic groups. OK, so this is the last result, or this is the last slide that I have. But just to finish up, so sort of as a continuation of this line of research, a natural thing to try to do would be to transfer our linear results to a nonlinear setting, namely to consider actions of these elementary subgroups on affine algebraic varieties. And a particularly nice class of actions to which our techniques are applicable are the so-called locally finite dimensional ones. So those are the actions for which, in the induced action on the ring of regular functions, every point has a finite dimensional orbit. And so it will be sort of interesting to try to analyze what kinds of actions are locally finite dimensional. And this would hopefully lead to some sort of analog, algebraic analog of the Zimmer program. OK, so thank you very much for your attention.